MarkAlain Déry. He's an infectious disease physician, epidemiologist, Chief Innovation Officer and Medical Director for the largest Medicaid providing system in Louisiana, Access Health Louisiana, and recognized nationally by the American College of Osteopathic Internists as the Internist of the Year in 2020. I did not know that. So congratulations on that. And of course, also a founder of a local community radio station, 102.3. MarkAlain, welcome back to the program. I'm here with Emma Vigeland, of course.
Hello, Sam, and hello, Emma. Thanks for being here, Mark.
Also, you are now the host of a podcast. Should we play that first? I want to play that segment because want to lead into these questions about the vaccinations, where we are, where we need to be in terms of herd immunity, and then ultimately, what constitutes the end of the pandemic. But first, let's lead in with your podcast here. It's animated. I like it. Here we go.
Hey-ho, let's go. I'm Dr. MarkAlain Déry, and I'm an infectious disease doctor and epidemiologist.
And I'm Doc Griggs, and I'm a community health specialist. Speaking of special, today's podcast is coming live from inside the human body.
So, Doc Griggs, does that make it a podcast?
Dude, don't make me regret sharing my space-time hop trick with you. Thanks, TV sitcoms.
So, these COVID-19 vaccines are super safe and effective, and thankfully, were developed quickly in response to the global pandemic.
First, let's explain how the coronavirus makes us sick. Ooh, check out those spike proteins on the coronavirus. They help it burst through healthy cells, where it replicates inside, destroying the cells and making us sick. I really hate that dude.
The vaccine will take care of him. Vaccines stimulate your immune system to fight viruses. Some of the COVID-19 vaccines work by delivering mRNA to your cells. Think of mRNA as instructions that activate the immune system.
Let's check out a healthy cell to see how mRNA works. The COVID-19 vaccines deliver a package loaded with millions of mRNA to your cells. Then the ribosomes read the genetic code on the mRNA like a manual and produce spike proteins that mimic the COVID-19 ones. That stimulates your immune system to make antibodies. Now, off to the lymph nodes.
Here's where antibodies are created. The heroes that fight coronavirus. The spike proteins attach to the antibody, leaving an imprint of the spikes, basically setting a trap for the nasty coronavirus.
When this part of the antibody attaches to these spike proteins on the coronavirus, it immobilizes the virus and stops it from infecting our cells and making us sick.
If an actual coronavirus comes into the body, the antibodies are ready to rumble. Battle faster! That's why COVID-19 vaccines are essential for teaching your immune system how to fight off the coronavirus.
And that's our show for the day. Ready to roll?
I've got this.
That is so great.
It is so great. I honestly wish I now feel like I should download that to my phone, and so we could just I walk around and explain this to people. But all right, so that's the mRNA.
Hold on, Sam. Can I just say real quickly? You actually kind of were the inspiration for that animation, because I think 2 times ago when I was on, you mentioned the vaccine and you were like, "Isn't this the stuff that science fiction is made out of?" Or you made some comment like that, and that was the first time that it occurred to me that people didn't really quite understand how the vaccine worked. And that kind of led to a series of events that ultimately led to that animation. But I wanted to say that when you said to me, like, again, 2 times ago when I was on, I think maybe in like late summer, you were like, aren't these vaccines the things that science fiction was made out of? And that planted the seed in my head.
Well, then it reinforces my belief that my ignorance can sometimes spur on great responses. So there we go. Well, thank you for that. So all right, wait a second. So what we saw was the mRNA. That is the Moderna and the Pfizer BioNTech. how does the J&J and AstraZeneca, which are the other two that we have, at least in this country, and AstraZeneca hasn't been approved by the FDA in this country as of yet, but how do they work? How is it different in the way that they work?
Right. So they use what's called an adenovirus vector. So what Dr. Kismike Corbet did at the NIH was that she figured out a way that was able to introduce the mRNA directly into the cell so that it got to the ribosome. And the ribosome is what I refer to as a 3D printer. And so that mRNA was able to get directly into that ribosome. And then the ribosome was able to make that photocopy and make those spike proteins. And so that was, when you said this is the stuff that science fiction is made out of, that is the part that you were referring to. You were like, really? You're going to just inject mRNA into the muscle cells and somehow mysteriously it's going to get into the ribosome? It did. It worked. And that was what was like, that was what so was mind-blowing about these vaccines. And we're going to start seeing a lot more vaccines based on this. Whereas the J&J and the AstraZeneca work on older technology. And what they do is they take an older, they take a virus, adenovirus. It's a virus that causes common cold. So it's very good in getting into cells. And what they did is they removed out the genes that cause the symptoms of a common cold. So they never trigger an inflammatory response. And what they're able to do is they're able to take they place instead of the genes that cause common cold, what they were able to put in there was the genes that cause the cells to make spike proteins. So it's one extra step. The mRNA just gets rid of the middleman, if you will, and goes directly to the ribosome, whereas the other vaccines go through the nucleus, and then from the nucleus it gets turned into goes from DNA to RNA, and then RNA goes to the ribosome. So it's a more complicated step, and that's one of the reasons why I think the mRNA vaccines work better, or they're more effective, because it goes directly to the ribosome, and from the ribosome it kicks out those spike proteins. And just one more thing, you'll see that I named it the vicious virus, and the reason why I did that was because I based the virus on Sid Vicious, the bass player for the Sex Pistols. So that's why you see the spike collar around the spike proteins, and then you see the little chains. And I'm a bass player, so but I was reminded, I sent some pictures over that. I was reminded of one of Sid Vicious's best quotes, and he said, there are two things that I love: beer and my reflection, which I think is a great quote. So anyway, so that was why we made the virus, so the vicious virus.
All right. Well, so just to be clear in terms of those two differences there, at the end of the process, they both create these spike proteins.
Yes, exactly.
So with the mRNA, what happens to the mRNA? Like
great question. It's like Snapchat. It's like the Snapchat of genetic material. As soon as it gets through the ribosome, it goes away immediately. So it's immediately, it never leaves the ribosome. It goes into the ribosome, and then it just disappears. But what it makes instead are those spike proteins, and those spike proteins then go into the lymph nodes, which stimulates the immune system to make antibodies.
And is it possible, and I'm just going over questions that people have asked me in the past where they get, sort of nervous or some of the sort of junk science that we hear out there. Is it possible that the mRNA trains the ribosomes in some way that they will react differently in the future to other, other possible infections, or will it ultimately impact the immune system of someone who has the mRNA vaccine?
Not at all. It's like trying to say, if you make a photocopy of something using your office photocopier, that whatever it is that you're photocopying is going to somehow change the machinery of that photocopy. That's just not, it's not founded in science or the physics of today. That just doesn't happen.
Well, and also we're hearing about the potential for more coronaviruses of this variation, right? Or that kind of, like, do you think any of this photocopying has impacts on potentially future coronaviruses?
No. Where that comes from, so the generation of variants, and so it's a great question, Emma. The generation of the variants actually come from people who are immunocompromised. And so people who are, so one of the things that we were going to talk about today was that there has not been a global equitable distribution of vaccines globally. We know that, right? And so because of the lack of equitable distribution of vaccines, you have certain countries like the US, we are the most vaccinated. So we've completed the most vaccines in the US. Israel and I think Hungary or what have you, they vaccinated more of their people, but they've all had one dose. But we're the country with the most complete vaccinations, either for one dose or for the 2-dose vaccines. So what happens is that when you don't vaccinate everybody equally, either here in the US, because we have people who are vaccine hesitant, or you have people around the world, like in India, there's 2% of the country that has been vaccinated. In the continent of Africa, there's been less than 1% of people who've been vaccinated. What happens is that for every one person the coronavirus infects, their body now becomes a laboratory, or lack of a better word, a petri dish, to create new coronaviruses, because once it gets in, it mutates. That's what it does. But it mutates the most in people who are immunocompromised. So people who have cancers, leukemias, this sort of stuff. And the reason is that their body's not able to produce antibody responses. So the virus is just able to reproduce. And what we've seen documented, and there was a great 2 articles, one at a New York City and one out of Brigham's Women's Hospital in Massachusetts, and at Boston, what they found was they were able to document 2 different case studies, and they found 2 different people, and they were able to document in these 2 immunocompromised men that over 6 or 7 months, they were making the variants that we're seeing today. Their bodies made the B117, which emerged out of the UK, and they also made the 1351, and which emerged out of South Africa, and P1 that emerged out of Brazil, out of South America. So essentially, it's people who are immunocompromised that are the ones that are generating these variant organisms.
All right. So, and I think Emma's question was slightly different, and I want to return to that in a moment. But just to pursue this, since we're here, so the idea, and we'll get into the sort of the more about the inequitable distribution of the vaccines, but the idea is that because the vaccine has not been widely, we're talking around the world and within this country too, to a certain extent as well, widely distributed, disseminated, reaching all the people that it has to, invariably, whatever the number is, 1 out of 1,000, 1 out of 1,000,000 of folks who are immunocompromised and catch COVID. That's the real problem. Is
that's right?
Okay, and so
that's exactly right.
It's not just that, like, if you let it spread over the course of a otherwise healthy population, you'll still have deaths. You'll still have all the problems associated with COVID, but the opportunity for variants comes when it has a host that can't fight it and can only fight it sort of a little bit, and so it sort of creates the incentive for the virus to mutate, but there's no end to that mutation within individuals.
That's exactly right. It probably happens in other individuals as well, but it's much, the rates are much higher in people who are immunocompromised.
Okay, and I think the question that Emma was asking about the mRNA was more about its ability to fight infections in the future. In other words,
yes.
Are there other coronaviruses out there that have a similar enough spike protein that the possible immunity I have from getting that mRNA vaccine will be like, oh, COVID 2022? Sorry, dude, your spike proteins are just like COVID-19, and so you're done.
Yeah.
So, Emma, I'm so sorry. That's such a great question. I apologize. I totally missed it. Yeah, so such a great question. So they are working. So initially, when they first worked on the Moderna, because that's what the NIH did, and then they sold that to Pfizer and BioNTech, essentially. And remember, Moderna has M and then RNA in the name. And in fact, they actually trade on the stock market as mRNA. So this was really made for the vaccines. They had hoped that they were going to make a class a vaccine that would have a class effect. So all the viruses, because remember, coronaviruses account for 15 to 30% of the annual common colds. So we're finding right now that that's probably not the case, that this spike protein is probably very unique to the virus that emerged out of Wuhan. And we refer to that as the wild type virus. And the way that we see that is we see that the vaccines aren't as effective. They're effective ish. We don't know 100% because we haven't seen real life data, but we know that they're less effective against other organisms that have emerged. Like I said, the 1351 out of South Africa and P1, and then possibly 1617 that has emerged out of India as well. So what they are doing right now, and so this is why it's such a great question, Emma, is just last week was the first evidence that emerged that they actually are trying to now work on a vaccine that has a class effect. So answering basically what you're asking. So ideally, that's where we want to go. We're not there yet, but we're working our way there.
Does the fact that and again, we should say, like,